Hello everyone, welcome to the next problem solving session for the novel technologies for food processing and shelf life extension course. In this session, we'll be discussing syllabus related to week 9. I hope I'm audible. In case I'm not, just kindly let me know. So, we'll solve problems related to week 9 syllabus. We'll start with the first question. If you guys have any doubts, you can post it in the in-call messages or you can unmute yourself. If you want me to repeat a question or go slower, you can let me know as well. Okay. Question 1. What is the respiration quotient for the following reaction? Tripalmitin, which is a C15 fatty acid, plus 145 moles of oxygen gives 102 moles of carbon dioxide plus 98 moles of water plus energy. So how do you proceed with this reaction? So before we go forward, do you guys know what is the respiratory quotient? Respiration quotient is used to respiration quotient is generally defined for a particular substrate, and that is defined as the rate of carbon dioxide produced by rate of oxygen consumed. So when you are looking at a respiration process, any organism for that matter will take in oxygen and then use a substrate, which could be either carbohydrates, it could be lipids, it could be organic acids, and so on. So there are multiple substrates, and that substrate along with oxygen is consumed by the organism, and then the resulting products are carbon dioxide, water, and energy. So for any respiration process, the respiration quotient can be defined as rate of carbon dioxide produced by rate of oxygen consumed. So with this formula in hand, what is the respiration quotient for this particular reaction? So if you want to answer as well, you can post it in the in-call messages itself, or you can unmute yourself. So how to proceed with this? It is already given that for every 145 moles of oxygen consumed, you have 102 moles of carbon dioxide. So you just have to substitute it in the formula. Respiration quotient is equal to 102 moles of carbon dioxide divided by 145 moles of oxygen, which gives you a respiration quotient of 0.7. So the answer is option C. So can a respiration quotient go above 1? Am I audible? So can a respiration quotient go above 1? Yeah. So when you're dealing with organic acids, the organic acids as your substrate, instead of the C51 fatty acid, if you are dealing with organic acids, yes, the respiration quotient can go above 1. When you are dealing with fatty acids and lipids, as in this case, tripalmitin is actually a triglyceride with 51 carbon atoms. So when you are looking at lipids as your substrate, your respiration quotient is less than 1, because as you can see here, the amount of oxygen is much lesser than that of your amount of carbon present. So when you have lesser amount of oxygen and more amount of carbon present, then it generally has a respiration quotient of less than 1. Sorry, I think I meant it the other way around. So if you have more amount of oxygen consumed and lesser amount of carbon dioxide produced, which is in the case of lipids. So in case of lipids, your carbon dioxide will always be lesser than that of your oxygen consumed. So in that case, respiration quotient is less than 1. In case of in case of carbohydrates, it is equal to 1, and in case of organic acids, it is greater than 1. So we'll discuss this question again towards the end as well. So that time we'll have a much clearer idea. So for this question, the answer is 0.7, which is option C. Okay. Question 2. Which of the following gas packaging system is suitable for both retail and catering packaging of meat, fish and prepared meals? So A, you have Gamela packaging system, B, deep draw machine system, C, flow pack machine system, and D, vacuum chamber machine system. So before we proceed, what is the purpose of a gas packaging system in food? So gas packaging systems are used in case of when you are trying to package fruits and other kind of meals, and you have a specific you do not require oxygen inside your packaging system. If you have a lot of oxygen inside your packaging system, this will result in oxidation processes and growth of bacteria and all. So in order to extend the shelf life of your food product, you make sure that you replace majority of the oxygen with nitrogen, which is an inert gas. So you will not have any kind of oxidation process that is happening. You will not have bacterial or fungal growth as well. So you replace oxygen with nitrogen and you increase the amount of carbon dioxide inside the package. So this is why you need to alter the atmosphere around the food system in order to extend the shelf life. So one is to prevent oxidation, second is to prevent the growth of bacteria. So for that we need to modify the gas around the food product, which is why you require a specific gas packaging system, and you have different kinds of systems available for different purposes. So you either have for retail packaging or you have for catering packaging process. So which of these packaging systems are used for both the retail and catering packaging? Retail is what you get it in small packets, that is easy for consumption, and catering is more of a bulk process. So which of these packaging systems is used for both the kinds of retail as well as catering packaging? So any clue which of these packaging systems are used? Okay, we'll go one by one. Deep draw machines are used for rigid and semi-rigid packages. When you're dealing with very rigid foods that are not very fluffy or so, we have deep draw machines that are used for rigid and semi-rigid packaging systems. So all these packaging systems basically have the same role, but then their application is in a different region. So deep draw machines are used for rigid and semi-rigid packages. You have flow pack machines that are used for flexible pillow packs, like say bread, biscuits and all. They are more flexible food products. So when you're dealing with flexible food products, you use a flow pack machine system where you change the oxygen inside those flexible food product packages. And these are known as pillow pack pouches as well, because they're pretty flexible and soft in nature. And Gamela packaging is used only for retail packaging. It is again used for all these meats, fish, except poultry and all, but it is used only for retail packaging. Whereas a vacuum chamber machine is suitable for both the retail and catering packaging of meat, fish, nuts and prepared meats. So based on what is your application, the size of the packaging system, the efficiency, everything changes. So a vacuum chamber machine system can be used for both retail as well as bulk packaging of meat, fish and prepared meals. So answer is option D. If there is any doubt, you can ask me to repeat the question again. Okay, question 3. We will now look at a numerical problem. Kiwi fruits stored in a controlled atmospheric storage unit produce ethylene at a rate of 0.1 microliter per kg per hour. the required ethylene concentration inside the storage unit is 40 parts per billion, then what will be the output capacity of ethylene decomposer in meter cube per hour for 2 tons of kiwi fruit with an efficiency ratio of 0.95? So before we proceed with the question, what is the role of an ethylene decomposer? Why is it necessary to decompose ethylene, especially in case of fruits? So, any doubts? Ethylene is a volatile gas substance that is released by fruits and vegetables, and this ethylene, this volatile gas, kind of in case of some fruits, this gas production increases over time after harvest. For in some cases, it is before the harvesting season. In some cases, it is after harvest. Your ethylene production increases, and this ethylene production will result in ripening of the fruits. So in case of banana or guava and all, after harvesting you can often see that it is very raw, but after a few days you can see it ripening. So this ripening with time is because of ethylene production. So when you receive the fruits in the market, you often see they are very raw. So it is often necessary to maintain this raw fruit between your harvest system until it is being supplied to the consumer. So let's say it takes 40 days from the time of harvest to reach it to the consumer. Till that time, you need to make sure that the fruits and vegetables that you're dealing with are not already ripened or in the stage of decay. So if ripening starts, then the decay process will also start pretty soon. So often sellers will try to prevent this ripening process till the product reaches the consumers, which is why ethylene decomposition is pretty necessary, so that you remove all the ethylene and prevent the process of ripening till it reaches the consumers. Once it reaches the consumers, you do not need any of these, and consumers will often prefer a ripe form of fruit. So till it reaches consumers, it is necessary to prevent the ripening of fruits, which is why ethylene decomposer is often used to remove the ethylene or to decompose the ethylene. So with that concept in mind, we'll start the numerical. So we'll start the numerical. Given here is the ethylene production rate of 0.1 microliter per kg per hour, and we have the required ethylene concentration, that is what is allowed inside the storage unit, is 40 parts per billion. It's a mistake here, is 40 parts per billion. The mass of fruit is 2 tons. The efficiency ratio is 0.95, and we need to find out the output capacity of the decomposer, which means we need to find out the output capacity of the ethylene decomposer unit in meter cube per hour. So for this, we have a formula. Is any of you aware of it? How to calculate the output capacity of a decomposer? So output capacity of an ethylene decomposer given by F is equal to R, which is the rate of the ethylene production, in microliter per kg per hour, M, which is the mass of the fruit, in this case the kiwi fruits, in kgs, C is the required ethylene concentration in parts per million, and D is the efficiency ratio of the ethylene decomposition, and F is the output capacity in liter per hour. So either you can substitute whatever values in these particular units itself and you will get the output capacity in liter per hour, or you can convert everything into SI units and the output capacity will also be in meter cube per hour. You can use both the ways. You can either convert everything into SI units, which is less of a confusion, and you'll already get it in meter cube per second, then you'll convert it into meter cube per hour. Or else you can substitute whatever values that you have in these units itself. Microliter per kg per hour, which is 0.1. Mass of the fruit in kgs. You have 2 tons here. When you convert tons into kgs, you multiply it by 1000. So 2 tons is actually equal to 2000 kgs of the mass of fruit. C is the required ethylene concentration in parts per million, not billion. So you have to convert 40 parts per billion into 40 parts per million. And D is the efficiency ratio, and when you substitute it in these units, you will get F in liter per hour. So we'll do that now. So F is equal to R is in the same units, 0.1 microliter per kg per hour. M is 2 tons, which when converted into kgs, you multiply by 1000. So 2000 kgs. C is the allowed ethylene concentration in parts per million. So when you convert parts per billion into parts per million, you multiply it by 10 power minus 3. So 40 into 10 power minus 3 into D, which is the efficiency ratio, which is 0.95. So when you simplify this, you get F is equal to 5263.16 liter per hour. And when you convert this into meter cube per hour, you multiply it by 10 power minus 3. So you get 5.26 meter cube per hour. Any doubt in this? You can either, if this is very confusing, you can convert all the values given into SI units. Then you will get it in meter cube per second. F, then you can convert it into meter cube per hour. That is also possible. If you want me to repeat this question, kindly let me know. The answer is option A here. Okay, moving on to question 4. When there is no increase in the respiration rate of the food material with changing the temperature, the value of Q10 is dash. So you have A10, B1, C0 and D infinity. So which of this is correct? So what is a Q10 value? So Q10 value is basically the temperature coefficient over 10 degrees Celsius intervals, or Q10 describes how the respiration of a commodity changes as the temperature is raised or lowered. So if you raise a temperature of a particular the environment in which particular product is placed in, the respiration rate of the food material will also change. Generally in a particular range it will change. So Q10 is basically the ratio of those rates. So let's say you have particular rate X at temperature equal to 10 degrees and you have a rate Y at temperature equal to 20 degrees. So the temperature interval is 10 degrees. You have 10 degrees and 20 degrees. So the difference in temperature should be 10 degrees. In that case, the ratio of the rate will give you Q10 values. So hope this is clear. If you have temperature equal to 10 degrees Celsius and then you have temperature equal to 20 degrees Celsius, in that case delta T is equal to 10. In that case, the ratio of the respiration rate is equal to Q10. So if over the temperature range, let's say at 50 degrees and 60 degrees, your respiration rate remains constant. In that case, the ratio of the respiration rates, since they are same, is equal to 1. So if there is no increase in respiration rate, your R1 and R2, that is your respiration rate at two different temperatures, will be equal. So R1 by R2 will be equal to 1. So in this case, the value of Q10 when there is no increase is equal to 1. So generally we find that the Q10 values are the highest between 0 degrees Celsius and 10 degrees Celsius. That is, you generally for a food product you get it at around 2.5 to 4, and then slowly they decrease to 1, when there is no change in the respiration rate and you are reaching a limit of a limit to which the tissue can handle. Let's say after 50 degrees the tissue cannot handle. That is, it will start undergoing thermal death. So in that case, in that range, your respiration rate will not drastically change and your Q10 value will be equal to 1 when you are approaching the death limit of the tissue. So hope this is clear. What is a Q10 value and when is it equal to 1? The answer is option B. Any doubts? Anything that needs to be repeated? Okay. Question 5. In a spray coating method, the spraying patterns deteriorate with A. Increase of fluid viscosity, B. Increase in operating pressure, C. Increase in fluid temperature, and D. All of the above. So which one of these is correct?
Option D.
Okay, do you think spray coating method deteriorate with increase in fluid temperature? It's not option D actually, it's a different option. So let's go one by one. So in the spray coating method, it's in form of an edible coating method where you coat your food products with some sort of edible coating that you can actually eat. So you have a food product and you'll have a nozzle that will spray the coat on top of the food, and then you can dry and then store the food product. So when you're spraying a fluid material, you need to make sure that the fluid can be easily sprayed or easily spread also. So in that case, you want your fluid viscosity to be as low as possible. So an increase in fluid viscosity will actually deteriorate the spraying pattern. So A is correct, definitely. But when you increase the temperature and increase the pressure, it is actually easy to handle the fluid. So if you, in a fluid with increase in temperature, you have a decrease in viscosity. That is the property of a fluid. This is the property of a liquid, sorry. In case of liquid, increase in temperature results in decrease in viscosity. And you actually want a decrease in viscosity to easily spray it into small droplets and then spread the coat. So you want as low viscosity as possible. So you need to increase the temperature and increase the operating pressure, but decrease the fluid viscosity. Hope this is clear. The spraying pattern deteriorates with increase in fluid viscosity because it becomes difficult to spread the coat, whereas it improves with increase in operating pressure and fluid temperature. So the answer is option A here. It actually gets better with increase in operating pressure and increase in fluid temperature, but with increase in viscosity, it becomes bad. So that is what her question is here. It needs to be easily spread across the surface of the food. So you need as low viscosity as possible, and this is maintained by increasing the temperature and increasing the pressure. The answer is option A. Only increase in fluid viscosity will hamper the spraying pattern. Otherwise, it is actually good for the spraying pattern. Any doubts? Okay. Question 6. In the edible coating technology, which among the following option shows the correct relationship between equilibrium spreading coefficient Ws, the adhesive force Wa, and cohesive force Wc? So we have different relations here. Ws is equal to Wa plus Wc. Wc is equal to Wa plus Ws. Wa is equal to Wc plus Ws. And Wc is equal to Ws divided by Wa. So what is the relationship between Ws, Wa and Wc? You can think of it logically as well. If you don't know the relationship, you can think of it logically, what an adhesive force does and what a cohesive force does and what is the equilibrium spreading coefficient. No, option A is not correct. So that there should be actually a balance between adhesive and cohesive force. So adhesive force is what will allow it to stick onto the food material and spread. So the spreading can be given by the adhesive force, whereas cohesive force is what will cause the coating to shrink. That is, cohesive force is more between the coating molecules. So if you have a polymer that is being coated on top of the food, the force between two polymer molecules is given by the cohesive force, and the force between the polymer and the food material is given by adhesive force. So adhesive force should actually dominate over the cohesive force for the coating to spread. If your cohesive force starts dominating, then everything, your coating material will shrink and it will not spread on top of the food material. So is the difference clear between cohesive and adhesive force? Adhesive is between the coat and your food product. Cohesive is between two coat products, two coat molecules rather. So the correct relationship between the equilibrium spreading coefficient, adhesive and cohesive force is Ws is equal to Wa minus Wc. Adhesive force minus cohesive force. So the balance between these two will give you the spreading coefficient. If adhesive force dominates, then the coat will spread evenly. If cohesive force dominates, then you have non-uniform spreading, which is not preferred. So then Wa is equal to Wc plus Ws, which is option C here. Hope this is clear. The difference between adhesive and cohesive force, the balance between these two is the spreading coefficient. Okay. Question 7. If you want me to repeat any of the question, kindly let me know. Which among the following material characteristics is not true for chitosan? A. High water permeability, B. High water resistance, C. Poor mechanical properties, and D. High gas barriers. So what is a chitosan and what are the properties? Any clue what is the correct answer for this? So chitosan is a polymer made up of, the answer correct is B. So I'll explain what is a chitosan. So chitosan is a polymer molecule of glucosamine. So it has repeating units of glucosamine. So this is a unit of glucosamine, and you have repeating units of glucosamine where one molecule is linked to the other molecule via beta 1 to 4 linkage. So you have beta 1 to 4 linkages of glucosamine, and these can be either acetylated or non-acetylated. So you'll have both, mixture of both in chitosan. So chitosan is a cationic polymer that is made up of glucosamines, and which can be acetylated as well as deacetylated. So the properties of chitosan are high water permeability and lack of water resistance. It does not have high water resistance. It has a lack of water resistance. It has poor mechanical properties and well as but high gas barriers. So this is often used as a polymer coat to prevent any sort of oxidation or unwanted reactions with the atmosphere or so. So in order to prevent oxidation, you often have a polymeric material made up of chitosan to prevent its exposure to the atmosphere. So the answer is option B. Question 8, which is a numerical. The orange juice is aseptically packaged in a laminated pouch and held at 25 degrees Celsius. The degree of browning as the optical density at 420 nanometer measured on the first day is 0.1 in juice. The browning reaction follows a zero order reaction. The rate constant for the juice browning is 2.375 into 10 power minus 3 OD per day. Calculate the shelf life of the juice in days if the juice becomes unacceptable when the degree of browning exceeds 0.3 OD. So in this problem, you have an orange juice and we are constantly measuring the optical density or the absorbance at 420 nanometers. So initially at day 0 or day 1, your absorbance or the OD at 420 nanometers is 0.1. And so you're storing the orange juice for over a time, and you have to throw the orange juice if the OD exceeds 0.3. And your rate constant of the browning reaction that causes this increase in OD is 2.375 into 10 power minus 3 OD per day. So you need to calculate how long you can store the juice before you can throw it because the OD exceeded 0.3. So how do you proceed with this? This is basic chemistry that you would have probably learnt. I mean, the concept you would have learnt it in your 11th grade, maybe 11th or 12th. So we'll look at the given first. Given OD at time t equal to 0 is 0.1 and OD at some time say t, that is what we need to calculate here. At some time say t is equal to 0.3. Your rate constant is equal to 2.375 into 10 power minus 3 OD per day. And we have been given that the browning reaction follows a zero order kinetics. So when you mean by zero order reaction, your dC by dt, that is your rate, is equal to K, which is your rate constant, into the concentration of C power 0. Had this been a first order reaction, you would have C power 1. Had it been a second order reaction, you would have C power 2. Since it's a zero order reaction, you have C power 0, which is equal to 1. So dC by dt is equal to K. Hope this is clear. This is the definition of any zero order reaction. So now when you integrate it from C0 to C and from time t equal to 0 to time t, you get C minus C0 is equal to K into T. So if you need to calculate what is the time t, T is equal to C minus C0 by K. Hope this derivation is clear, where C is the concentration or anything that you are measuring at say time t. C0 is at the initial at time t equal to 0, the concentration at time t equal to 0, and K is your rate constant. So we already have what is C, which is 0.3. So above 0.3 you have to discard the orange juice. So the maximum concentration that you can let it go, or maximum OD that you can let it go, is 0.3. C0 is already given as 0.1, that is at time t equal to 0, and the rate constant is also given in the question. So all you need to do is just substitute it. So 0.3, sorry. So 0.3 minus 0.1 divided by 2.375 into 10 power minus 3. So this, since your rate constant is already in OD per days, you will get the time also directly in days, which is 84.2 days. Is this clear? Any doubts in this question? Any doubt in the derivation also? So answer is option D. If you want me to repeat any question, kindly let me know. Question 9. Which of the following options indicate the correct flow line for preparation of edible coating material? You have 3 different steps here. One, you have addition of glycerol, you have addition of sodium alginate with continuous stirring, and you have heating in water bath. These are the 3 steps involved. So which comes first? What is the first step in the preparation of an edible coating material? So when you're trying to make an edible coating material, first you take water, then you add something known as a sodium alginate, which has the ability to polymerize and form a polymer kind of material. So you take water, You add sodium alginate and you continuously stir it in the presence of heat. So addition of sodium alginate with continuous stirring is your first step. Then you start heating it in a water bath and then continuously stirring. So it will turn into a transparent solution. So first you will have some white color kind of a powder dissolving. Once it starts dissolving in the presence of heat and the presence of stirring, you will get a transparent solution. To that transparent solution, you will add glycerol. So that will be your coating material. In that coating material, you will use different kinds of methods to dip or to spray your food product. That food product you will dry it and then store it. So this is the entire process of an edible coating technology. First you will take water, add the polymer, which is the sodium alginate in this case. You will continuously stir it and heat it to dissolve it and make it transparent. And then you add glycerol and then you coat the food product, you dry it and then store it. The answer is option C. Question 10. Which of the under mentioned ethylene scavenger can be incorporated into a plastic film structure commonly used in fresh produce packaging? So you have A, palladium chloride, B, nanosilver, C, charcoal and D, zeolite. Which of these is the correct answer? Actually, all of these, the common thing between all of these is that all of these can be used as an ethylene scavenger. That is, in order to prevent ripening of your fruits, you have to have an ethylene scavenger. That is, it will either absorb all the ethylene or it will decompose all the ethylene that is present. So you need an ethylene scavenger in your food product to prevent it from ripening. So all four of these do act as an ethylene scavengers, but its application as a plastic film is different for each of the cases. So different compounds can be used only in certain forms. All of them cannot be made into plastic films. So minerals such as zeolite and active carbon or pumice can be incorporated into the plastic film structure commonly used in fresh produce packaging. So you can just mix it along with the plastic film itself, and that film itself you can use for packaging. Such minerals are intended to scavenge the ethylene and also modify the gas permeability of the film so that carbon dioxide can diffuse faster and oxygen can enter more readily. So you need a particular kind of a gas or an atmosphere around your food product. As I discussed in the previous slides, you need carbon dioxide and less of oxygen. So you need to accordingly you need to make sure that the permeability of your package is also different. So in this case, minerals such as zeolite will not only act as an ethylene scavenger, but it will also help in modifying the gas permeability of the film so that this can prevent any sort of oxidation process that is happening. Whereas the rest of the options given here, nanosilver can also be used as an ethylene blocker, but not as a packaging, not as a plastic film. They are used as an absorbent pads that are placed in the trays of fresh cut fruits and not in the packaging structure. So all of these four options are ethylene scavengers, but all of them cannot be incorporated as a plastic film. Only zeolite can be incorporated as a plastic film. Nanosilver can be incorporated as absorbent pads, whereas palladium based scavengers, also having good ethylene absorption capacity, are used as sachets in packages or in storage rooms. Answer is option D. Charcoal is in fact used directly as you would have known, charcoal is actually used directly as a particle that will absorb all the ethylene. It cannot be used in a plastic film. So zeolite is the only thing that can be incorporated as a film, whereas the rest of them can be used as an absorbent pad or a sachet. So the answer is option D. Hope this is clear. Question 11. This is numerical again. So a cold storage facility measures 6 into 6 into 3 meters, that is length, breadth and height, as 6, 6 and 3 meters respectively on the inside, and is constructed of bricks laid in a cement mortar. So the wall thickness that is made up of bricks is 40 centimeters, and there is a 10 centimeter thick cork insulation on the inside of the four walls. And on top of that, you have a cement plaster as well, which is 1 centimeter thick. So you have three layers here. You have a brick, you have a cork insulation, and you have a cement plaster. The heat transfer coefficient for the ceiling is 20% more than that for the walls. The outside temperature is 30 degrees Celsius and the inside is maintained as 5 degrees Celsius. Calculate the total heat load in kilocalories per day due to conduction. So the thermal conductivity of the brick, cork and the cement plaster, that is the three layers, are 0.45, 0.025 and 0.25 kilocal per hour per meter degree Celsius respectively. So you need to find out what is the amount of heat load, or what is the conduction, or the rate at which the heat is transferred out. So heat is transferred in terms of kilocalories per day. So how do you proceed with this? What law do we use here? So we use what is known as a Fourier's law of conduction. So we'll first discuss what is the given here and then we'll proceed to the formula. Given here, let's say first layer is your brick, second layer is your cork, third layer is your cement plaster. So the thickness of the brick wall x1 is 0.4 meters, which is 40 centimeters. I am converting everything into SI units here. Thermal conductivity of brick, which is K1, is equal to 0.45 kilocal per hour per meter degree Celsius. Second layer, the thick cork, thickness is 0.1 meter and thermal conductivity is 0.025. Thickness of the cement, which is the third layer, is 0.01 meters and thermal conductivity of that is 0.25. Outside temperature is given as 30 degrees Celsius and inside temperature is given as 5 degrees Celsius. So with this, do you know how to proceed with this? What is the formula used? Okay, look at the formula first. So in this case, when you're looking at heat transfer, your heat has to be transferred from the wall, then to the cork, then to the cement plaster. So you have three layers. So the thermal conductivity, the effective thermal conductivity will vary because you have multiple layers here. So when you're dealing with a multi-layer system, you can find out the effective conductivity, effective heat transfer coefficient as follows. So 1 by U. U is the overall heat transfer coefficient. Now here you are looking at overall heat transfer coefficient because you have multiple layers of walls, or rather multiple layers through which the conduction is happening. If you had a single layer, then this will be directly equal to K1 or K2 or K3. That will be equal to K. But since you have multiple layers here, the overall heat transfer coefficient of the multiple layers can be defined as 1 by U, which is the heat transfer coefficient, is equal to x1 by k1 plus x2 by k2 plus x3 by k3. So if you have 5 layers, there will be plus x4 by k4 plus x5 by k5. So depending upon the number of layers, you will have x1 by k1 plus x2 by k2 plus x3 by k3 and so on. So you have all this given in the question. All we need to do is substitute it. So 1 by U is equal to, for the brick wall, 0.4 divided by 0.45. For the cork insulation, which is 0.1 divided by 0.025. And then for the cement, which is 0.01 divided by 0.25. So is anybody calculating, or should I just proceed with this? Should I go slow? If you want me to go slow, just kindly let me know. Post it in the messages, please. So this is how you calculate the overall heat transfer coefficient combined for all the layers. So with this, you get, when you simplify this, you get 1 by U is equal to 4.928. So U is equal to 0.203 kilocal per hour per meter square degree Celsius. So the units of U and K are different. So kindly note that. For K it is just meter degree Celsius. For U it is meter square degree Celsius. So with this U, with the overall heat transfer coefficient, you can calculate what is the heat conduction. First through the walls. So the heat transfer can happen through the 4 walls also. It can happen through the ceiling as well. So you need to calculate the total heat conduction through the walls plus heat conduction through the ceiling. So we'll look at one by one first. The heat conduction through the wall, we'll first calculate the area of the walls. Area of the walls is equal to 4 into area of the one wall. So you have 4 walls, we are not considering the bottom. We have 4 walls, so 4 into area of one wall, which is equal to 6 into 3 meters, is equal to 72 meters square. So this is the area of all the walls that is present. The heat transfer through the walls is equal to UA into T outside minus T inside. So any heat transfer, this is actually the Fourier's law of conduction. So just a minute. Okay, so the heat transfer through the walls can be given by the heat transfer coefficient into area into delta T. This is applicable for either if it is a wall or a ceiling or any surface. So through any surface, heat transfer this is the generic formula. Heat transfer can be given as U, which is the heat transfer coefficient, A, which is the area, and T outside minus T inside, which is the delta T. So when you substitute this, you have U as 0.203 kilocal per hour per meter square degree Celsius. You have the area of the 4 walls, which is 72 meters square. Outside temperature is 30 degrees Celsius, inside temperature is 5 degrees Celsius. So 30 minus 5. So if you solve this, you get heat transfer through the walls as 365.4 kilocal per hour. When you convert it into per day, you multiply it into 24, which is 8769.6 kilocal per day. Is this part clear? We have as of now calculated only the heat transfer through the walls. You calculated the overall heat transfer coefficient because you have multiple layers. That then you calculate the area of the walls and then you substitute it into the generic formula. So this is for the walls. We still have to calculate the heat transfer through the ceiling. So in order to calculate through the ceiling, it is already given that the heat transfer coefficient of the ceiling is 1.2 times or 20% more than the heat transfer coefficient of the walls. This is given in the question. So the heat transfer coefficient of a ceiling is equal to 1.2 into 0.203. This is what we calculated in the previous slide. So since it is 20% more than that of the coefficient of walls, you multiply it by 1.2. So the heat transfer coefficient of the ceiling is different, which is 0.2436 kilocal per hour per meter square degree Celsius. Hope this is clear. This is given in the question that it is 1.2 times more. So the heat transfer coefficient of a ceiling is different, which is 0.2436 kilocal per hour per meter square degree Celsius. So now you substitute it back into the same formula after calculating the area. So heat transfer through the ceiling is again the same formula, UA into delta T. You substitute U of the ceiling, which is 0.2436. Area is 6 into 6. So if you remember the cuboid structure, you have 6 into 6 into 3. So this is the structure of the room. So the ceiling is area is 6 into 6. So that is what we are doing here. 0.2436 into 6 into 6, which is your area, into 30 minus 5, which is your outside temperature minus inside temperature. So the heat transfer through the ceiling alone can be simplified and it is given as 219.24 kilocal per hour, which when you convert it into day, that is you multiply it into 24, you get 5261.76 kilocal per day. Hope this is clear. If I am going too fast, kindly let me know. We can repeat the question again. So the overall heat transfer through the entire storage unit is equal to conduction through the walls plus conduction through the ceiling. So the conduction through the walls is what we calculated in the previous slide, which is 8769.6, and conduction through the ceiling is what we calculated right now. So the summation of this is 14,031.36 kilocal per day. So this is your heat load or total heat of conduction that is asked in the question. Answer is option A. So is this clear? Any part of the formula which is unclear or anything that needs to be repeated? Okay. So if there is no doubts, I will proceed to the next question. Question 12. Dash is used as an active substance for moisture scavenging in active packaging system for maize to reduce aflatoxin contamination. A. Bentonite, C. Sodium polyacrylate, C. Calcium chloride, and D. Sodium chloride. So before we proceed, what is an aflatoxin? So aflatoxins are toxins that are produced by fungi, generally aspergillus and so on. So often your maize has all these fungal growth, and because of this fungal growth, it often produces something known as aflatoxin, and hence the maize becomes unfit for consumption. So in order to reduce this aflatoxin contamination, you need to reduce the moisture to prevent the growth of fungus as well. So you prevent the moisture, this will prevent the fungal growth, this will again prevent the aflatoxin production. So amongst these four products, sodium polyacrylate, that is the polyacrylate sodium salt, shows potential for grain drying in reducing the aflatoxin contamination, particularly in developing countries. So people often add sodium polyacrylate to the maize during the drying process, which will scavenge all the moisture and prevent the fungal growth and toxin production. Whereas the other three, the bentonite, calcium chloride and sodium chloride, are used as active substances for decreasing the moisture content as well as reducing the browning index in mushrooms and other materials, not for grains. So all of these are also used for moisture scavenging but have a different application. The answer is option B here. So question 13. This is pretty similar to what we had in the question 11. A plastic package made of LDPE and PET has a surface area of 400 centimeters square. The thickness of each layer of the film is 10 millimeter and the partial pressure difference of the oxygen across the film is 0.21 atmosphere. So here you are not dealing with thermal conduction, you are dealing with mass transfer. The permeability coefficient of LDPE is 4.18 into 10 power minus 8 centimeter cube centimeter per centimeter square second atmosphere, and that of PET is 1.67 into 10 power minus 10. So calculate the rate of oxygen transfer through the package. So in question 11, where we were dealing with thermal transfer, that is the heat transfer, in question 13 we are dealing with mass transfer, but the overall concept will somewhat remain pretty similar. So instead of conductivity, you are given here permeability. So given here, the thickness of each of the layer is 0.1 centimeter. Since all of the units are in centimeter, we'll convert millimeter also in centimeter. So thickness of each of the layer is 0.1 centimeter. The surface area of the packaging material is 400 centimeter square. The difference, that is the delta P across the film, is 0.21 atmosphere. So had it been a thermal conduction, you have delta T. In this case, since it is mass transfer, it is delta P, which is 0.21 atmosphere. The permeability of one layer is 4.18 into 10 power minus 8. Permeability of the second layer is 1.67 into 10 power minus 10. Again, here you are dealing with multi-layer. So you will have to find out the effective permeability. That is what we are going to do here. So generally, the rate of oxygen transfer can be given as P into A into delta P. Here P, small p stands for permeability, A stands for area, delta P stands for the pressure difference, and X stands for the thickness. This is very similar to your thermal conductivity formula, where if you take P in the denominator, you have A into delta P divided by X by P. So this is ideally in your thermal conductivity was U. This was equal to 1 by U in case of heat transfer. In case of mass transfer, this will be your effective mass transfer coefficient. So if it's confusing, you can let it go, but it's very similar. If you look into the formulas, it will be very similar for the heat transfer as well as mass transfer. So to proceed with this, if you take P permeability to the denominator, you have X by P here. You have area into delta P, which is your partial pressure difference. So again, since you're dealing with multiple layers, X by P, which is effective for all the layers, is equal to X1 by P1 plus X2 by P2. So this is for the LDPE layer, this is for the PET layer. To substitute it, it is already given as each of the layers are 0.1 centimeter thick. So you have 0.1 divided by permeability of the first layer, that is 4.18 into 10 power minus 8. Then you have for the second layer, which is 0.1 centimeter thick, divided by 1.67 into 10 power minus 10, which is the permeability of the second layer. So this will give me X by P, the effective X by P for both the layers together. So when you calculate or simplify this, you get X by P as 6.012 into 10 power 8 centimeter square second atmosphere by centimeter cube. Hope this is clear. Is this clear, or do you want me to repeat any part of it? So the rate of oxygen transfer, now you have to just directly substitute. Area is already given, delta P is already given. You now found out the effective X by P. That is equal to 400 centimeter square given in the question into 0.21 atmosphere divided by 6.012 into 10 power 8. So this will give me the rate of oxygen transfer as 1.39 into 10 power minus 7. This will be in the units of centimeter cube per second. Answer is option D. Any part of the question that needs to be repeated? Okay, if there are no doubts, I move on to question 14. Which of the following is used as a sterilant for spices? A. Ethylene oxide, B. Chlorine, C. Sulfur dioxide, and D. Ethylene gas. So which is the right answer for this? What is used as a sterilant for spices? We'll start one by one. Chlorine is used to bleach the floor and sanitize the equipment. So chlorine is not used. Chlorine is also a sterilant, but that is not used for spices. And sulfur dioxide we had discussed in one of the previous problem solving sessions. Sulfur dioxide is often added to inhibit the enzymic browning in dried fruits. And ethylene gas is the gas that we discussed here. It's a volatile gas that promotes the ripening of the fruits, whereas ethylene oxide is used as a sterilant for spices. So chlorine and ethylene oxide are sterilants, but chlorine is used for flour and sanitizing the equipment and the surface rather than food. It's more used as a surface sterilant, and ethylene oxide is used as a sterilant for spices. So answer is option A. Question 15. Which of the following satisfies the condition of ultra low oxygen storage? So you have different concentrations of oxygen here, 1 to 1.5 or 0.5 to 1% oxygen, and you have different concentrations of carbon dioxide as well, either 4 to 5% or 2 to 3%. So you need a perfect combination of these oxygen and carbon dioxide for the ultra low oxygen storage. So which of these is the correct option? So in an ultra low oxygen storage, as I discussed before, the entire point of reducing the oxygen is to prevent first growth of microorganisms, and second thing is to prevent any sort of oxidation process that is happening. And third thing, it is also used to prevent respiration processes. So if your food has a certain respiration rate, so respiration rate increases, then all your ethylene production will also increase, and it will also decrease the shelf life. That is, your food will slowly start to die as well at some point. So you need to make sure that your food is present in either high concentrations of carbon dioxide along with low concentrations of oxygen. So the ULO storage uses oxygen levels close to the minimum level required for the maintenance of the plant tissues. So you have a minimum, depending on the kind of food product that you are dealing with. Each kind of food will have a minimum oxygen that it can use to survive, and a maximum amount of carbon dioxide. So if you go beyond this range, that is, if you lower the oxygen too much or if you higher the carbon dioxide too much, two things will happen. First thing is that it will start to undergo necrosis, because plant tissues need some basic amount of oxygen to survive. If you reduce that also, it will start browning and it will cause necrosis or cell death. That is, your rupturing of the cells will start happening. So you don't want browning or necrosis or the death of tissues, and at the same time you do not want any sort of anaerobic fermentation. So when you don't have much of oxygen present, it will often lead to anaerobic fermentation, and it will give a very alcoholic flavor to your food. So you don't want those as well. So you need to maintain oxygen at a basal level possible. That will help in the maintenance of the plant tissues, but it will prevent any sort of other oxidation or unwanted process. So that, in case of food products, is generally in the range of 0.5 to 1% oxygen. And carbon dioxide should always be higher, which is 2 to 3%. So this is what is preferred for an ultra low oxygen storage. If you go beyond this range, it will lead to browning, necrosis, as well as anaerobic fermentation. So the answer is option D here, sorry. So hope it is clear what happens when the oxygen level drops drastically. Okay, moving to question 16. Which of the following chemicals helps in reducing the post-harvest ethylene production in fruits? So you have A. ethylene hydrazide, B. 1-methyl cyclopropene, C. cetyl pyridinium chloride, and D. potassium sulfate. So which of these chemicals helps in reducing the post-harvest ethylene production. So certain fruits like banana, guava, and all keep ripening even after you harvest it. This is because your ethylene production keeps on increasing. So you need to reduce the ethylene production till it reaches the consumers, and this is done by the addition of chemicals. So which of these chemicals is used as and used to reduce the ethylene production? So 1-methyl cyclopropene is the ethylene action inhibitor and delays the changes in the changes caused by the plant hormone ethylene. So plant hormone basically causes ripening and softening and color changes in fruits. So if you prevent ethylene, then you can prevent all these changes as well. So what 1-methyl cyclopropene does is, your plant tissues will have receptors on its surface. So 1-methyl cyclopropene will bind to these receptors and inhibit the production of ethylene. I'm sorry, it will inhibit the action of ethylene, not the production. So ethylene will bind to the receptor and cause these changes. So if it competes with ethylene for this receptor, so this chemical will bind to the receptor and it will not allow ethylene to bind. So the moment ethylene cannot bind to its receptor, you will not see these changes. I hope the mechanism of action is clear. So these two are competitors. Ethylene and 1-methyl cyclopropene are competitors for the same receptor. So when you add the chemical, ethylene will no longer be able to bind to the receptor, and all these processes such as ripening, softening and color changes will be prevented. So this is the mechanism of action of 1-methyl cyclopropene. The answer is option B. Okay, moving to question 17. In tal prolong, fruits are coated by A. palm oil, B. nylon, C. CMC and D. acetic acid. So which of these is the correct edible coating for the process of tal prolong? So one way of covering fruits to prevent them from ripening is known as tal prolongation. So these are covered with often kind of polysaccharides. So in a tal prolongation, you cover the fruits with some kind of a sugar or a polysaccharide. So in this case, out of the 4 options, CMC is the polysaccharide, which is carboxymethyl cellulose. So fruits are coated with carboxymethyl cellulose, which is a polysaccharide, and this is a water soluble anionic compound with linear long chains. So the reason why this is preferred is because CMC is tasteless, it is odorless, and it's a free flowing powder that is white to cream in color. It can easily spread also because it is a free flowing powder. So because of these desirable characteristics, plus it is edible in nature, we use the process known as tal prolongation to cover the fruits and to slow down the ripening process. So the answer is option C. So sorry for this. So carboxymethyl cellulose is the product that is used in the process of tal prolongation, which is tasteless, odorless and free flowing, which are all desirable characteristics of an edible coating. So hope this is clear. Question 18, which is a smaller numerical. So if you remember what we discussed about Q10 value, you will be able to answer this question. The zero order rate constant for the degradation of ascorbic acid in dried vegetable packed in a laminated pouch is 0.0745 mg per 100 gram uh, week per week at 30 degrees Celsius and 0.0255 mg per 100 gram week at 20 degrees Celsius. So calculate the Q10 value for ascorbic acid loss. So do you remember what a Q10 value is? So the Q10 value, sorry, just a minute. So the Q10 value is the fractional change in the rate with every 10 degrees Celsius rise in temperature. So you have a 30 degrees Celsius, you have a 20 degrees Celsius. So you can see a 10 degrees rise in the temperature. So the fractional change in rate, that is the ratio of these rates, is equal to the Q10 value. So Q10 is basically rate at temperature at say T plus 10 divided by rate at some temperature T. So this is how you calculate a Q10 value. So we substitute the values. Q10 is equal to 0.0745, which is at 30 degrees Celsius, divided by 0.0255, which is at 20 degrees Celsius. So the answer is 2.92, which is option D. So here you can see the Q10 value is greater than 1. If your Q10 value is equal to 1, which means both the rates are same. Which means that with respect to temperature, there is no change in the rate. That is when your Q10 value is equal to 1. So hope this is clear. How to calculate the Q10 value. Okay, question 19, which is also numerical. Calculate the amount of heat in kilojoules that must be removed from 1 kg of raspberries to cool it from 25 degrees Celsius to minus 5 degrees Celsius. The moisture content of the raspberries is 81%. Assume that out of that 81%, 27% of the total moisture does not freeze. That is, it will still remain in water form and it will not freeze to ice. The specific heat of the raspberries above the freezing point is 3.7 kilojoule per kg degree Celsius and below the freezing point is 1.86 kilojoules per kg degree Celsius. Assume the latent heat of freezing as 335 kilojoule per kg. So what is the total amount of heat required to cool down the 1 kg of raspberries is the question. So how do you proceed with this? So here there are 3 processes involved. First thing is that you are cooling the raspberries from 25 degrees Celsius to the freezing point, which is 0 degrees Celsius. Then you have conversion of water into ice crystals, that is the latent heat of freezing. Then after that you will further cool it from 0 degrees Celsius to minus 5 degrees Celsius. So there are 3 processes. One from 25 to 0 degrees Celsius, then the latent heat of freezing, then 0 to minus 5 degrees Celsius. So 3 processes involved. So we need to calculate the amount of heat at 3 of these processes to calculate the total amount of heat. So given here, the amount of raspberries, that is the mass, is equal to 1 kg. Initial temperature is 25 degrees Celsius. Final temperature is minus 5 degrees Celsius. Moisture content is 81%. The fraction of that moisture that do not freeze is 0.27. So the fraction of moisture that does freeze is 1 minus 0.27, which is 0.73. Hope this is clear. So you can apply the latent heat of freezing only to the moisture that is able to freeze. That is equal to 0.73, that is 1 minus 0.27. So the Cp above freezing point is 3.7 kilojoule per kg degree Celsius. The Cp below the freezing point is 1.86 kilojoules per kg degree Celsius. And the latent heat of freezing is 335 kilojoule per kg. So in order to calculate the total amount of heat, that is equal to heat removed during the cooling to the freezing point plus the latent heat of freezing plus the heat removed from the cooling during cooling from the freezing point to the final temperature. So 3 different processes involved. So we look at the formula for each of the processes. So for total heat is equal to, for the first process that is from 25 to 0 degrees Celsius, formula can be given as mCp into delta T, which is Ti, T initial minus 0 degrees Celsius, plus this is for the freezing process, that is for ice to turn from liquid to crystals, that is given by mass into the fraction of moisture that can be frozen into lambda, which is your latent heat of freezing. So m is mass, xf is the amount of moisture that can be frozen into lambda, which is your latent heat of freezing. So this is the second process. Then you have the third process, that is your cooling from the freezing point to minus 5 degrees Celsius, which again can be given as mCp and into 0 degrees Celsius minus the final temperature. So hope this formula is clear. So we have everything given in the question, we just have to substitute it. So the total heat is equal to 1 kg of raspberries into 3.7, which is your Cp above your freezing point, into 25 degrees Celsius, which is your initial temperature, minus 0 degrees Celsius. So this is your first process. Then second process, which is 1 kg of raspberries, which is mass, into xf. So xf is the total amount of moisture that can be frozen, which is you already have only 81% of moisture, which is 0.81, into 0.73 is the one that can be frozen. So hope this part is clear. Out of 81%, 27% cannot be frozen. So rest is 73% can be frozen. So 0.81 into 0.73 is your xf. And lambda is given as 335 kilojoule per kg. Then you have the third process, which is 1 kg of raspberries into 1.86, which is your Cp below the freezing point. And then you have 0 degrees minus Tf, which is your minus 5 degrees. These are the three processes involved. So if your freezing point was something else, if it was not 0 degrees Celsius, accordingly this formula will also change. If your freezing point was 2 degrees, you will write it as 2 here. And since you are assuming a freezing point as 0 degrees Celsius for water, you have 0 here. Hope this is clear. Then when you simplify this, for the first process it is 92.5 kilojoules. For the second process it is 198.08 kilojoules. And for the third process it is 9.3 kilojoules. The total amount of heat that needs to be removed to cool down the raspberries is 299.88 kilojoules. Answer is option B. So any doubt in this, the three processes and the formulas? Any part that needs to be repeated again, kindly let me know. Okay. So moving to the last question. The value of the respiration quotient is dash if the substrate is a lipid. So which one of these is correct answer? So this is similar to the first question that we discussed in the class. So which of these is correct? What is the respiration quotient for if the substrate is a lipid? So if a substrate is a lipid, the respiratory quotient, which is equal to the amount of carbon dioxide produced by amount of oxygen consumed. That is the formula for RQ or respiration quotient. So for a lipid, RQ is always lower than unity because the ratio of carbon and oxygen in lipid is lower than the ratio in carbohydrates. So since your oxygen is always higher than your carbon, your RQ will always be less than 1 for a lipid. Whereas in case of carbon dioxide, the amount of carbon and oxygen are the same. So RQ is equal to 1 in case of carbohydrates. And when you're dealing with organic acids as a substrate, your C by O ratio is greater than 1. So your RQ is also greater than 1. Hope this is clear. You can refer back to the first question again, which is a numerical based on RQ only. So RQ is normally assumed to be 1 if your metabolic substrates are carbohydrates. So the answer to this question is lower than unity or lower than 1. So that's all for today's problem solving session. If you guys have any doubts, you can post it again in the group messages. We can discuss the question again. Or you can also post it in the discussion forum or mail me again if you have any doubts. So thank you.